Okay, so welcome everyone to the SIAM Activity Group Imaging Science Best Paper Prize 2020. I'm Carola Schönlieb, I'm the current chair of the SIAM Activity Group of Imaging Science. And before I hand over the prize to the word to the most important person in the room at the moment, I will say a few words about the prize and also the prize winner. So the SIAC Imaging Science awards this Best Paper Prize every 2 years to the authors of the best paper as determined by the prize committee on mathematical and computational aspects of imaging broadly interpreted. Previous recipients of the prize are in 2012, Rodrigo Palma Amestoy, Eduardo Provenzi, Marcelo Bertalmio, and Vincent Casellas. In 2014, Alfred Bruckstein, David Donohoe, and Mickey Elard. In 2016, Jonathan Aflalo, Ron Kimmel, and Dan Raviv, and there was no award made in 2018. The selection committee for the 2020 award consists of Gitta Coutinho as the chair, Julian Chang, Omar Gattas, Stefan Wild, and myself. The SIAC IS Best Paper Prize is awarded in 2020 to Gregory Buzzard and Charles Booman, Suhas Srihari, Singanallur Venkata Krishnan, Bernd Wohlberg, Lawrence Drummy, and Jeffrey Simmons for the paper on plug-and-play priors for bright field electron tomography and sparse interpolation that was published in IEEE Transactions on Computational Imaging in 2016. The award recognizes the contribution in this paper, which for the first time plug-and-play priors have been used for solving a challenging inverse problem such as electron tomography, alongside a profound convergence analysis. This publication has inspired various follow-up works, either using the approach in combination with other methods or providing high-quality reconstructions for diverse imaging applications. Charlie Booman will present the prize lecture today. And before I hand over to you, Charlie, I'll just say a few words about you. Charlie is the Showalter Professor of Electrical and Computer Engineering and Biomedical Engineering at Purdue University. He received his BSEE degree from the University of Pennsylvania, his MS degree from the University of California at Berkeley, and a PhD from Princeton University in 1989. Charlie's research is in the fields of computational imaging and applications ranging from medical to scientific imaging. His research resulted in the first commercial model-based iterative reconstruction system for medical X-ray computer tomography, and he is co-inventor on over 50 issued patents that have been licensed and used in millions of consumer imaging products. Among many other things, Charlie is editor-in-chief of IEEE Transactions on Image Processing. He led the creation of IEEE Transactions on Computational Imaging, is a member of the National Academy of Inventors, and was the 2014 recipient of IS&T's Electronic Imaging Scientist of the Year Award. The title of his talk today is Plug and Play, a general approach to AI and sensor model fusion. I very much look forward to your lecture. The word is over to you.
Thank you very much. It's truly an honor today to be able to represent the group of outstanding collaborators and researchers that were co-authors on this paper. So Greg Buzzard is from Purdue University in the math department, and I particularly want to thank him for doing a spectacular job of making slides, I think, that illustrate some of the really abstract conceptual ideas really clearly. Brent Wahlberg from Los Alamos National Laboratory, who is an outstanding collaborator. Venkata Krishnan from Oak Ridge National Laboratories, and Jeff Simmons and Larry Drummy from AFRL. and Suhas Srihari from Wells Fargo. So, and I just want to acknowledge that the support, financial support we've gotten from Los Alamos, Oak Ridge, AFRL, and NSF, and the Alert Center, DHS Center at Northeastern University. So, okay. So I'm going to start off with some, a little bit of background, remedial background that I'm sure you're familiar with to create a little context for the problem. So the inverse problems, the central problem of inverse problem is how do you reconstruct an object or an image or some unknown quantity from physical measurements of a physical system. And the classic example of this is tomography, in which you have sinogram measurements of an object. This is done in medical imaging like CT imaging. And from these measurements Y, you want to recover X. So the Bayesian perspective is that you have a forward model, which is a probability distribution for the measurements Y given X. And then you have a prior model, which is the probability, assumed probability distribution for the unknown image X. And from those two things, you want to solve the inverse problem. And you can think of this as a regularized inversion method or as map estimation. But basically what happens is that you formulate an optimization problem. And there are two terms in the optimization problem. The one term is the negative log probability of the data given the unknown. So this is called the negative log likelihood. And then here, this is the negative log prior distribution. And your goal is to minimize the sum of those two terms. This first term here enforces fitting of the solution to the data, and the second term enforces regularity in the solution. So this is a regularized inverse problem, and this is the methodologies we used when with GE Healthcare's MBR system that was done in 2011 for CT reconstruction of volumetric CT for medical applications. So all is good. I mean, this sort of framework has been used now for years, been widely adopted, and people really like it. So life is good, but so what's the problem? But the problem is, what about what we're going to call algorithmic models? So these days, everybody uses things like deep neural networks and other kinds of algorithms that don't fall into this simple framework of cost function to be minimized. Instead, they represent actions you apply on objects. So you, in a deep neural network, it may take an image in and it produces an image out. So how do you merge those two views of the world? So in order to discuss this, I want to talk about this idea of model types. So traditional physical and statistical models involve a cost function that you minimize. So the cost function represents some sort of fitting to the data. And the goal then is to find a value of X that minimizes that cost function. Example would be like least squares estimation or total variation regularized inversion. And this also fits naturally into a Bayesian framework using map estimation. But sort of an emerging view of the world, which is becoming more and more popular, is what you might call algorithmic models. So this is kind of a very different thing, because you give it, the algorithm, some input and it produces an output. So a deep neural network may process the image in some way. It can denoise it. That's going to be one of the most common things that we'll talk about, but there's many other kind of operations you can perform. And the key idea here is that the input and the output space are the same. But in this case, there's no explicit cost function being minimized. And examples would be like BM3D, denoisers, neural networks. And it's easily applied, but it's not exactly clear how these fit together. So the key challenge that this talk is addressing is, how do you fuse models, model fusion? People have talked about data fusion for, I don't know, 30 years, 40 years, but this is really a little bit different because this is fusion of models, okay? And the traditional models are physical models, involve cost minimization, but now these new models that are becoming more and more prevalent are what we call algorithmic models that have an input-output relationship. So how do we fuse heterogeneous models? That's the key question that we're going to try to answer. So now plug and play is sort of the, and oh, by the way, I forgot to mention that Yves Romano gave a talk before this and was really excellent. I hope you saw. If not, maybe you can go back and see the recording. So he set up a really nice framework for what I'm talking about today. And he discussed the red algorithm, which I won't have time to get into in a lot of detail today. But he also mentioned plug and play. So plug and play then is this core of of this publication that we had. And also it's sort of the jump off point for a number of things we've done that I'm going to talk about. So really, and the idea is that plug and play is a meta algorithm. So it's an algorithm that you use to construct algorithms, and it's a way of fusing heterogeneous models. And it also has the outcome that it's one of the side effects, which is very important in my opinion, is it creates modular reconstruction algorithms, which can be implemented in modular software, which is really important. And then it's also the starting point for something I'm going to spend some time talking about today, which we call MACE. Multi-agent consensus equilibrium. And MACE is sort of, I'll propose as a framework for understanding plug and play. Okay, so this talk will be about foundational concepts. You're not going to see a lot of experimental. I obviously am believe very much in experimental results and really showing that things work on real data, but there's not going to be a lot of time for that today. So you'll hopefully just have to trust that these the methods of plug and play are useful. So I apologize for that, but I really want to focus on the big picture ideas, the theory. So, okay, so here's the overview of the talk. First, I'm going to talk about the roots of plug and play in terms of regularized inversion and their interpretation of thin manifolds. And then I'll talk a little bit about variable splitting and proximal maps, which are very important to understand, the ADM algorithm. And then I'm going to introduce a concept which we call an agent, which is sort of a generalization of proximal maps. And then I'm going to talk about the actual plug and play family of algorithms and describe how it is really a meta algorithm and how it works. But this sort of raises the question, which I think Yaniv actually raised in his talk also, which is the plug and play algorithm is great, but what does it mean? I mean, how do you interpret it? Okay. And then our interpretation, we're going to pose this framework, which we call multi-agent consensus equilibrium, or MACE, as a framework for understanding plug and play, and also a framework for generalizing plug and play. But I'd like to emphasize something, which hopefully you'll find interesting, which is MACE is not just a method or an algorithm or a theory. It's really a lifestyle, okay? It's kind of a way of thinking about problems. So we kind of jokingly say that it's the MACE lifestyle we like to adopt. Okay, so the roots of plug and play. So regularized inversion, variable splitting, and proximal maps. Okay, so we're coming back to the problem again that we have the map estimation. So here what happens is we have, in a traditional forward model, we formulate the forward model as this represent the output as a function of some input. So in this case, the output is a linear combination, a linear transformation of input. So this might be a tomographic projection operator, as plus some, say, additive Gaussian noise, so that the model has an input and the output is the data. Now, in the regularized inversion framework, you kind of shift your view on that, and from that model, you extract a different kind of model, which we call here f of x, which is the negative log likelihood. So the input is the image, and the output is this cost function then, which is a function of x, and it represents how well we fit the data, okay? And then we do a similar thing with the prior distribution here, where we have the negative log prior. So a typical case would be that we'd adopt h of x here to be the total variation regularization. So you can interpret that as the negative log prior for some probability distribution. And then you put those two things together, and you now get the map estimation is formed by the minimization of the sum of these two terms. F is the data fitting term, and H is the prior modeling term, okay? So you want to both fit the data, but you also want to create a smooth or regular or reasonable reconstruction, okay? So, okay, now, the interpretation of this physically, or in the space, is that there's the values of F that are smallest define what we'd like to call a thin manifold. So, and the reason we call it a thin manifold is it isn't really a manifold of zero thickness. It has some width to it because of the noise that's in the system. So, but the minimizing F drives you to be on this manifold. Now, if the number of measurements you've made is less than the number of unknowns, so if you have 1,000,000 pixels, but you only have 1,000 measurements, then there's going to be 1,000,000 minus 1,000 dimensional subspace on which the solution can lie, and then the answer is very non-unique. Okay, so in addition, then you bring in H. So H is the prior. So the minimum of H defines a thin manifold in the image space, which represents the behavior of real images in your application space, and usually that's not linear. Okay, that would generally not be linear. And then your goal is to find a point which is balanced between these two. So it's as close as possible to both of them. And that's how that's achieved by minimizing the sum of these two functions. Okay, so now I'm going to introduce variable splitting. For you, those who know variable splitting, this will be a little remedial, but it's nice to go over it again. So the variable splitting is sort of a counterintuitive algorithm, but very powerful. So your goal is to minimize the sum of these two functions. So to do that, what you do is you actually try to minimize them separately. So if you notice, I kind of love this. Okay, so you replace H of X with H of V. So now this seems like a bad thing to do, because now you've doubled the dimensionality of your space you're doing the optimization on, because you have to minimize over X and V. But you add the constraint that X equals V. The advantage of doing it this way is that often methodologies for minimizing F are very different than the methodologies you would use for minimizing H. So by decoupling them, you can get more efficient optimization. And the classic example of this is the ADMM algorithm. So ADMM stands for alternating directions method of multipliers, I'm sorry. And the basic idea in ADMM is you alternately minimize F and H separately, but then you have an augmented Lagrangian term for communication between X and V that enforces this constraint that X should equal V. And one of the key ideas that makes ADMM work is this idea of proximal maps, which I'm going to talk about. So proximal maps, what is a proximal map? So the idea of a proximal map is you take this function F, which you're trying to minimize, and then you add an additional term to it, which is like a penalty term that penalizes the change in the solution, and you minimize it jointly. So the interpretation of this is that you start at some base point X, and X is the input to the proximal map. So uppercase F here is the proximal map, its input is X, and then you minimize these terms. You don't get all the way to the bottom because of this term over here, which looks like a spring that's forcing you to remain close to the base point. So there's two terms. There's the minimization of the base function here, which is f of z. Okay, so that's the function you're trying to minimize. And then there's this quadratic distance penalty. And then there's also this term here, sigma squared, which controls how much tension there is on this spring. So if sigma is small, then you're pulled close to the initial point. And if sigma is large, then you can move close to the minimum. So you start at the base point, the proximal map, the input to the proximal map is x, the output to the proximal map is f of x, and f of x then reduces the cost function, but it doesn't go all the way to the minimum. Okay, so now you can do this proximal map concept for both the forward model and the prior model, and the terms look the same, but it's interesting that for the prior model, what happens is that the proximal map, if you're familiar with these kinds of expressions, has the same form as a map estimator for a denoiser with additive Gaussian white noise using H as your prior model. So in other words, this term here looks like the log likelihood function, the negative log likelihood function associated with additive Gaussian white noise of variance sigma squared. So H has the interpretation of being a denoiser, okay? And now then the ADMM algorithm is formed by repeatedly applying F and H. So F is the proximal map for the forward model, H is the proximal map for the prior model. You just keep repeating these. Now you have to add this additional expression here for U. U has the interpretation of being related to the Lagrangian variable. So as you iterate this thing, the hope is that U will converge to a value that drives X and V to be equal, enforces the constraint, okay? So, so here's a key idea. Proximal maps convert cost functions to algorithmic models. So remember, our goal here from stated in the beginning is that we want to be able to handle heterogeneous models, models that are traditional cost function based models based on physical sensors, and models based on agents or algorithmic models. Okay, so we're going to introduce this idea of an agent. So the proximal map converts a cost function into an action, because what happens then is that by solving this optimization, the f of x takes an input of x and produces an output of f of x. So it changes this cost function into an action, okay? Now understand, okay, so we want to now generalize this idea of a proximal map to a more general concept of what we call an agent. So an agent is really a very simple idea, but I think a very powerful idea, okay? An agent is a function which takes an input and produces an output in the same space. So intuitively, the input is, say, an image or some other kind of object. Let's say it's an image, okay? So then the agent takes the image and produces a new image. And the concept of an agent is that you give it something and then it gives you something back that's a little bit better. Now notice I have the words better in quotes, because what does it mean to be better? Well, it depends on the agent. I like to think of agents as being like people. So if you have a company and you have a lot of vice presidents in the company, then each vice president is responsible for some different thing. So there might be the chief financial officer or the chief operations. So one vice president is in charge of reducing costs. The other one's in charge of improving quality of the product. Okay, so they don't necessarily have the same idea of what better is, okay? But they each have their own idea of what good is or better is. And that agent has that property of making things better, okay? So now then the agent is an algorithmic map, but it's more general than a proximal map. So proximal maps are agents, but agents are more general than proximal maps. There are agents that are not proximal maps, okay? And the classic example, or the common example that I think what Yaniv pointed out in his talk earlier is the example of the denoising agent. A denoising agent makes, from its point of view, makes the image better by taking away the noise, but it's not necessarily a proximal map. If this thing is a BM3D, then BM3D doesn't necessarily reduce any cost function, and it's not necessarily a proximal map, okay? So, okay, now I'm going to get into the actual family of this sort of background. Now I'm going to get into the family of plug and play algorithms. Okay, so now the big idea in plug and play is really kind of subtle, which is that this H operator, I argued, is really a map denoising algorithm method in the classic approach of map estimation. So why not just replace it with a more general agent that may not be a map estimate, may not be a proximal map. So the concept is just throw caution to the wind and just plug in your favorite denoiser in for H and see what happens. This gives you the advantage that you can use state-of-the-art denoisers. And obviously, there's been enormous progress in denoisers, and most of them don't fit into the framework of optimization, so why not use them? And that also produces a modular software system. Okay, so now this is the really cool thing. Okay, what we're going to do now, you're going to see the magical transformation from ADMM to plug and play. So ADMM algorithm alternates proximal maps, and plug and play alternates agents. So the only difference is it's the same algorithm, but the only difference is its interpretation, that you replaced proximal maps with agents and then suddenly it became PMP, okay? And okay, and now we have this really cool thing that makes a funny sound. It's sort of fun to watch. I particularly like this because I'm from New Jersey, and we had, like, I was kind of basically a motorhead growing up. And this reminds me of a piston engine and a muscle car or something, V8 engine. So it goes from F to H. So first applies the forward model, then it applies the prior model, it applies the denoiser, and then it updates the Lagrangian variable, and it keeps iterating, and hopefully it converges to something, okay? But, you know, you're not exactly sure. So PMP is actually a meta-algorithm. It's an algorithm you build on top of algorithms, okay? And it uses agents in place of proximal maps in your favorite algorithm, and you just plug, that's why we call it plug and play, because you just plug in your favorite denoiser and other algorithmic map and get the new PMP variation, okay? And here is like, these are not obviously state-of-the-art results. These are the results Venkat generated years ago when we wrote the first conference paper. And he just downloaded denoisers from different people's web pages and solved a simple problem of interpolation for sparse samples. And we found that we got amazingly good results. And also we found that the quality of the real results depended a lot on the specific denoiser. This would have been, this result here is the result we would have gotten using the classic map estimation, which was definitely not the best. And BM3D did a really great job in this particular example as a prior model. Okay, so that was a very encouraging. So now we were trying to publish various papers and we submitted, and there was some pushback from the reviewers, and one of the reviewers who has to this day remained anonymous, I just love this reviewer's comments, because they said, well, maybe instead of calling it plug and play, you should call it plug and pray, because you really don't know what's going to happen. So, you know, it was a valid concern. So it turns out, and this is sort of a foreshadowing, that I'm going to introduce this methodology called MACE. And with MACE, we can show now that sufficient conditions for convergence of P and P are that F and H are non-expansive. There's some additional very fine technical conditions, but basically it's just that they're non-expansive or strongly non-expansive. But the intuition is that with each iteration, when you apply F, you move closer to the center manifold. When you apply H, you move closer to the image manifold, and you kind of bounce back and forth, and U forces those iterations to get sort of smaller and smaller until hopefully you converge, and you do converge in this case. One thing to point out is that a necessary condition for this convergence, it is not necessary that F and H have a self-adjoint gradient. That means that their curl is not zero. And that's a necessary condition for F and H to be proximal maps. So that means that this algorithm will converge even when F and H are not proximal map. And that's very interesting, because that means that there's no cost function you're minimizing in that case. Okay, so what is the interpretation? Okay, here I'm just taking a side trip quickly to mention that these are the original two papers that we had on plug and play. So this was the conference paper at the Global SIP in 2013, and this is the paper that we're quite honored to get this award for today. But I just want to point out that there's been a lot of generalizations of this, and I'm sure there, there's other people who are much more knowledgeable about some of these technical methods, but there's been a primal dual generalization, there's FISTA, there's a stochastic gradient descent, there's incremental ADMM, and there's linearized ADMM. Of course, there's RED, that's a little bit of a different branch, but maybe that you would consider that related also. And then there's been lots of applications and all kinds of, actually Brent Wahlberg compiled this list of all these various publications that have used this. And it really gets quite good results in some real applications. So, okay, so what's the problem? Okay, well, it's pretty clear that I kind of raised the issue that people are concerned about, well, what is the problem? PMP is based on an optimization algorithm, but there's no optimization being solved. So what is it doing? So what problem is PMP actually solving? That's a huge question. And also, is there some way of formulating the solution which specifies what you're doing that's more coherent? And also, what if you have more than two agents? This is sort of a practical issue, but the classic PMP only has a forward model and a prior. What if you have more agents that you want to integrate? Okay, so that brings us to this concept of MACE, which we think is sort of a unifying theoretical framework for both understanding PMP and also generalizing it. And it's described in a SIAM Journal of Imaging Science paper in 2018 that we called Plug and Play Unplugged, Optimization-Free Reconstruction Using Consensus Equilibrium. Okay, so going back to the idea of the proximal map. Proximal maps take cost functions and convert them to agents. Okay, that's fundamentally what they do. And P&P use that framework as a way of integrating these heterogeneous types of models. So cost function model with an agent-based model. Okay, so now, okay, we can think of this as a matrix, okay? And I think this is really interesting and subtle. So I want to spend a little time on it. That this is a 2x2 matrix. So the first row of this matrix represents cost function based methods. Okay, MAP is a cost function based method. ADMM is an algorithm for minimizing cost functions, okay? But the columns of this matrix, this column represents criteria or problem formulations. And this column represents algorithms or algorithms for solving problems, okay? So ADMM, for example, is an algorithm and it solves the map estimation problem. The map estimation problem is a criteria. There are many ways you could solve it. And it may just be one particular method, the ADMM, and it uses proximal maps, okay? So now, but now the second column over here, the second row over here is the agent-based rows. So everything along this row should be something involving the use of an agent. So plug and play basically fits in here. It's the generalization of ADMM to the use of agents, but it's no longer necessarily minimizing a cost function. It's an algorithm that generalizes ADMM to the use of general agents rather than just proximal maps, okay? But that begs the question, what belongs in this piece of the matrix? Like something's missing here, right? So what is that thing? First of all, what should go here? Well, whatever goes here, first of all, it should be a criterion rather than an algorithm. So it should be a problem formulation or criterion, and it should be a criterion based on agents, not cost functions, okay? And it should also be consistent with, it should sort of fill out this thing. It's almost like a Sudoku puzzle, right? That it should whatever goes here should generalize map estimation, but it should also be the criterion associated with the algorithm P&P, right? So it should be the thing that P&P is solving, okay? And we claim that that thing is MACE, multi-agent consensus equilibrium, okay? So I'm gonna now sort of motivate the basis of MACE. So MACE is to ask the question, how do we reconcile multiple agents? So rather than starting with cost functions, we start with agents. So an agent takes an input, produces an output, and it enforces its sense of what is good, okay? So how do we find a solution which makes all the agents happy in some sense, okay? So, okay, we claim there are two things you need to make the agents happy. One is that you need the agents to have a consensus, okay? And the second thing is that we need equilibrium. So we need consensus and we need equilibrium. Okay, so what do I mean by that? Okay, let's look at consensus first. So now in this 2D example, the agent takes an input and it produces an output. So we can think of it as a vector in a high dimensional space. So x1 is its input, and then this is its output. So we get a bunch of arrows. Now in this case, the agents are not in consensus because they're all pointing to different points. But if we change the inputs, okay, we can force the outputs to all match. So in this case, the agents are all in agreement. They're all in consensus. So we want to change the inputs so that they all agree. So that's the consensus constraint. Okay, now in this case though, there's something wrong because imagine that this agent is in charge of reducing cost and this agent is in charge of improving quality. Well, if they both kind of think we need to move in this direction, we can make them both happier by moving this way. So it's not just that they should be in consensus, it's also they should be in balance, okay? And that means that the arrows, if I average out the vector arrows, they should really average out to 0. So we call that equilibrium, okay? So the agents are in equilibrium if the arrows average out to 0. So here are the equations that represent that. I mean, you can look at them, but basically each of these terms represents the difference between the input and the output. And the difference between the input and the output, we represent as u, as these variables u. So I have minus u here because that represents the change from, minus u is the distance from the output to the input. So u is the distance from the input to the output. So anyway, so this is the consensus condition over here, and this is the equilibrium condition, is that the vectors have to all sum to 0. if they sum to 0, then they also average to 0. Okay, so the average of the vectors has to be 0. So we get these two constraints that we can make some simple mathematical manipulations, and we get that x star is this output point that they should all agree on, and we get this set of equations. So we get an equation which matches each agent with the average of the inputs to that agent. So okay, so here's how it works. Now we can define a simpler notation for this by stacking the vectors. So we define W as being the X's are the inputs to each of the agents. So if we stack up all the inputs, we get this object W, okay? And then if we apply F to W, that we do that by applying F to each element of each corresponding agent to its input. And then this G operator, which is super cool, and I could spend a lot of time talking about it, simple but super interesting, is formed by averaging all the inputs. So all the outputs of the G operator are the same, and each output is the average of all the inputs, okay? So let me kind of, so then we can rewrite the equations in this sort of simpler form. F of W equals G of form. So this is the equation that defines the multi-agent, the MACE solution. It's the multi-agent consensus equilibrium solution. And just to go, I mean, it went by maybe a little bit fast. Oh, so this answers the central question then of how do we balance, how do we find an equilibrium point between sets of a set of n agents? And this is the equation we claim that you should solve. Okay, now, oops, that's really fun. Okay, I'm going to do that again because I like the sound it makes. Okay, this is MACE. Okay, MACE. So MACE is this thing. It could be like, I don't know, a club thing like this, or it could be something else, but we like to think of it that way. Okay, so here's, I want to just go over it one more time because I know it kind of could have gotten confusing. So F here then is the stacked operator that represents applying each agent to each of its corresponding outputs. And G is just this equilibrium agent. What it does is it just takes all of the inputs, it averages them and redistributes them. This can be viewed as in the form of a supercomputing, or as what they call map reduce, or in this case, it's a reduction followed by a broadcast. So this, and we've actually implemented this on large scale supercomputers, like the NERSC computer at Lawrence Berkeley National Labs. Okay, so the equation says that each agent's output should be the same, and each output should be the average of the inputs. Very simple, okay? So now coming back to this thing here, and the question is, what falls into this block here? What should be here? Well, we claim what should be there is MACE, multi-agent consensus equilibrium. And why do we claim that? Okay, well, in order for our claim to be substantiated, this should be, MACE should be a generalization of MAP, and it should also represent the criterion that's solved when you run the P&P algorithm. Well, it turns out that, not too surprisingly, this is going to be true. So if we, okay, let me do that one again. So in the ADMM algorithm converts to the P&P algorithm by replacing proximal maps with more general agents, right? That's how we got the P&P algorithm. So then the question is, oops, I went the wrong way. The question is, if is MACE a generalization of MAP? And the answer is yes, because when the agents are proximal maps, then the MACE condition here is exactly the same as the zero gradient condition for the minimization of the map function. So this is a sufficient, a necessary condition for solving the map equations. Okay, and then from the other point of view is MACE the criterion that P&P solves? And the answer is yes, because it turns out that any fixed point of the P&P algorithm solves the MACE equations, okay? So it's a generalization both ways. So we like to say that MACE here is completing the square. It's sort of the missing piece in this viewpoint of the world, okay? And okay, so now there wasn't time to go into a lot of detail, but there's some generalizations. You can do MACE in subspaces that's practical in certain cases. You can generalize the case of what it means to be consensus and equilibrium. And in fact, you can interpret, there's a modification of it in which you change the common output to be the midpoint of outputs that you can express the red conditions. And you can also, and we do this a lot, you can use different ways of computing the average. So we typically use a weighted average, which makes a very simple way of controlling regularization. But you can also use nonlinear combinations. It just has to have certain conditions which are usually met. So, okay. And, but one thing I want to point out is that if you vary from the basic case I told you here, then the generalizations in the map estimate and the completing the square piece may not hold anymore. Okay, so perspectives on MACE. So I haven't talked at all about how to solve the how to solve this equation. And I actually think that's a strength of the method, because you can go off and find your own algorithm for solving the MACE equations, and it might be a lot faster, particularly for your application. We typically do it with man iterations using fixed point methods, which I won't have time to go into, but that results actually in the P&P algorithm as a special case. Okay, and then also MACE gives a way to understand and formulate problems associated with existing algorithms, and also to formulate new problems. So, okay, so the takeaways are this. Plug and play, we believe, is a meta algorithm. It uses algorithmic agents in place of proximal maps, okay? And it generalizes the concept of minimization to equilibrium conditions, okay? MACE is a framework for thinking about plug and play, which in terms of consensus and equilibrium, it also generalizes plug and play to multiple agents. And we believe that MACE sort of completes the square. It represents the generalization of the map estimate, and also it's the condition that the plug and play algorithm is solving for. So, and it provides a mechanism for doing analysis of convergence. So at this point, thank you very much, and I'll be happy to entertain questions.
Thank you so much, Charlie. That was really interesting, very inspiring. Thank you. So while people, may I just remind everyone again that they can ask questions via the Q&A box or via the chat. And we already have some questions here in the chat.
Okay, maybe you could, I don't know how to get
them. Do you want me to unmute them, Charlie?
Yes, please. That would be my preference.
Okay, so Abdullah, if you are okay, I'll allow you to talk now. Abdullah, you want to ask your question?
Yeah. So I'm wondering about can you hear me?
Yeah.
Okay.
Yes.
I'm wondering about the connection between MACE and consensus ADMM, because it looks like both are solving multiple models or multiple penalties, and
yes.
both sort of averaging. But if that is the case and there is a connection, it's not clear.
Yes, there is a connection. Yes, absolutely. Yeah, that's an excellent question. Yeah. So let me kind of, I'm sorry, I'm having a little trouble with this.
Could you comment on how does that answer what we are minimizing explicitly? Because it's not clear what we are minimizing.
Okay, so let me go back to this viewpoint, okay? So it turns out MACE is the relationship of MACE to consensus ADMM is the same as the relationship of plug and play to ADMM, okay? So the MACE is the generalization. Well, first of all, MACE is a criteria. So whereas consensus ADMM is an algorithm, okay? So, but the consensus ADMM algorithm can be used to implement a solver for the MACE equations, okay? In fact, it falls out of the basic analysis. And it turns out that, well, there's a lot of different consensus ADM algorithms, but the basic consensus ADMM algorithm turns out to be a special case of the man iteration for for solving the MACE equations. So MACE is a generalization in the sense that consensus ADMM is an algorithm for solving optimization, whereas MACE is not necessarily solving optimization, it's solving for an equilibrium condition.
I see.
Did that help?
Yeah, it does help. I get it. But how does that answer one of the main questions about plug and play what functions, what cost function or what penalties are we minimizing? I guess your answer
You're not.
Is
I mean, that's a crucial point. That plug and play, let's take plug and play because it's a simpler case. plug and play can be convergent even when it's not minimizing any cost function, okay? There is no cost function. That's why it has to be formulated as an equilibrium condition. So the equilibrium condition works when there's a cost function, but so here with agents, the solution is we get an equilibrium condition, okay? Oh, yeah, okay, maybe it's better. So it's a generalization in the map estimate. It works in the case of the map estimate, the algorithm works, and in that case, special case, it is solving an optimization problem. But in the more general case, it's solving an equilibrium condition, okay? And the equilibrium condition, there is no corresponding optimization problem. It's not that you're solving. Mm-hmm. What I'm saying is, I'm like, some of my points here are a little bit, imprecise, because saying the precise thing is a little too complicated fast, okay? But it's true. Let me just put the equation up. So the key idea is this. It's kind of slow to go through these lines. Let me say this one more time. Okay, here you're not solving an optimization problem. You're solving an equilibrium condition. Here's another way to think about it. When you solve a PDE, for instance, let's say you solve the wave equation, okay? Boltzmann, Maxwell's waves equations, okay? When you solve that wave equation, you're not necessarily solving an optimization problem. You're just solving an equation. It's an equilibrium condition. So the consensus equilibrium is an equilibrium condition. In some special cases, it can correspond to an optimization, but it's more general.
Nice. Could I have a second question?
Yeah. Sure. Well, yes, I'm not the moderator, but it's fine with me.
That's fine. We have one other person who wants to ask a question, but yeah.
Okay, so for me, having a cost function is give me more intuition about how to design a criteria for images or for signals. In your opinion, how does the equilibrium notion gives, like, how could we design operators?
No, that's an excellent question, and frankly, I think it's an area for further research. So one way is that I'm not going to try to switch through the slides because it's too painful. But when you do have a physical model for one of the agents, like the sensor model, then it's a good idea to use to derive the correct proximal map. So that piece of it is a proximal map. Okay, but then for example, in plug and play, the prior model, you may use something that's not a proximal map. Like for instance, BM3D is not a proximal map, right? So in that case, if you put together a sensor model like least squares fitting to tomography data, okay, and together with BM3D as your prior model, the combination of the MACE solution, right, is well defined. Okay, but it no longer corresponds to an optimization problem. So your question is, how do you pick those things? So in the case of the prior model, you can, the classic strategy is that you do self-training where you try to learn an optimal denoiser for white Gaussian noise. And for the prior model, for the forward model, you can use a proximal map. But in more general cases, yeah, it's a good question. How do you design agents which lead to solutions which have optimality properties in the sense of the quality of the reconstruction? There's open questions.
Thank you.
Mm-hmm.
Thank you so much, Abdullah. So the next question comes from Celine Aslan. And I will also try to, Celine, you should be able to talk now. Yeah.
Hi. Okay, can you hear me?
Yes. Yes.
Okay.
Thank
Hi,
you.
Charles. Great talk. Thank you so much. I actually have a very straightforward question, maybe, and I hope you can just help me understand this. So I know PMP is motivated, like you give this proximal map, and it's like with denoising additive like Gaussian noise. And I wonder what if we have Poisson noise added, then and I know actually there's a paper, but I don't want to change the framework of the plug and play. So if you can elaborate on that, can we still use the same framework?
Yes. Or I mean, there's a variety of ways you can do it, but maybe the simplest way is that the forward model you take as the log likelihood for the Poisson noise. Okay.
Yeah.
Okay. Yeah, so you take it as a log likelihood, and then the prior model agent, you do a Gaussian noise denoiser. Now, this is one thing that's very counterintuitive for people, because they say, well, hold on, if I'm trying to get rid of Poisson noise, why am I training the denoiser from Gaussian noise? And in fact, it's ideal Gaussian noise, okay? Yeah. Well, because that turns out to be, fall out of the mathematics of computing the map estimate. So in theory, it works, that's the best thing to do. Now in practice, people have observed empirically that sometimes you don't get the best results in that case. That you can, and what people are finding is that in special cases, I think, well, I'm forgetting exactly who, but a number of well-known authors have studied this and find that you can optimize these agents to get better results for specific problems that go beyond the basic theory of just saying train on white Gaussian noise, okay? But a complete understanding of that, I think, is not yet known, okay? Which is a good thing, because I think there's a lot of interesting directions to take this research in. Okay, Alejandro Foy was working on that, and somebody else, but a number of people have looked at that, and we've actually observed that also, that sometimes you want the agents to play well together. So it's like the difference between an all-star team where you get each player to be the best, okay? Okay, versus a team that sort of plays well together, okay? And the theory of how that works, I think, is yet to be fully developed, okay?
But, yeah, I mean, I was just wondering, because, you know, like in like real experiments, like that would like not be possible. And I'm actually personally using PMP and it works great, but I was just, you know, like listening your talk, it just popped to my mind, like, am I actually like, you know, if I'm not training on like Gaussian noise, but yet the, you know, like I can still be able to implement the framework, well, you know, like I'm actually.
Yes, yeah, okay, let me put it this way. I think that one of the key ideas here is that this is kind of a certain freedom, okay, in this approach. That, hold on, what am I doing? Oh, I'm going the wrong direction. The idea that these agents, okay, the point is that you can, you know, you can pick the agents out however you want. Yeah. And sometimes you have physical intuition into the problem. And so you pick these agents in some way. So the theory, baseline theory says that, say you have two agents, one's a forward model and the other one's a denoiser. But in practice, you may know, okay, I also have this kind of artifact, so I want this agent to get rid of that artifact. And the beauty of MACE is you can just throw more agents in. Actually, there's going to be a follow-on talk by one of my students, Malia, on tomography, in which she knew certain things about the problem, and she just put in 5 or 6 different agents, each of which enforced some constraint that she knew that would be useful for her problem, and she got good results, okay? So it gives you a certain flexibility. You could say it's kind of ad hoc, maybe, in some ways it is, but it also gives you a framework that's modular, where you can put things in that you know are useful for your problem.
Okay, thank you so much. If there's no other talks, I can ask like very quick question as well, a follow-up. Is that okay?
I'm not the moderator, but it's fine with me.
Okay. So, you know, like when we say like, okay, like return X and return V, right? So in practice, like ADMM, like, you know, nobody solves until converges. I guess like all these papers I'm seeing, right? So we are actually solving like the sub-problems, like approximately and returning V. So like, you know, when we put this, like you're, you know, in your algorithm, so you're still returning V, but like, I feel like intuitively, like X equals V is not like really satisfied. Like, would that be correct?
Well, in practice, what happens is that sometimes, I mean, okay, so in MACE, okay, I haven't talked about the actual algorithm at all, is the problem, because there wasn't time. But there's an algorithm which is very similar to plug and play, okay? And basically, these are the conditions you're trying to solve, right? And when you run this iteration, and it gets pretty close. Now, the convergence of the algorithm depends, the sufficient condition for convergence of the algorithm is that this T operator, which is formed by the agents in a way that I haven't described, is got to be non-expansive, okay? So for real algorithms, you know, because they might have high gradients at points of discontinuity, maybe you get some hunting around and you won't get convergence like to double precision accuracy, but it gets pretty close. Like it'll get within, you know, a few percent of convergence. So, and if you have you know, and there's new methods which allow you to build neural networks with bounded, you know, gradient, that's not the word, but you know, and then you would just get numerically stable convergence to double precision accuracy. Okay, so yeah, it will converge, but if you throw something like BM3D in there, you know, maybe it'll hunt around a little bit.
Okay.
Yeah.
Thank you so much.
You know, thank you for the questions.
So before we close, just two things I wanted to share. One is that I've just been cured by Mickey from my ignorance, Charlie, that your daughter is in fact Katie Bowman.
Yes, she's better known than I am.
So it seems that this wonderful capability of producing super cool research lies in the family. So it's that's a fact I wanted to share, although probably many people in the audience have known this anyway already. And then the second thing, sorry, Charlie. Yeah, the second thing before we close is just to congratulate you again very much for the best paper prize. Very well deserved, and great talk. Thank you very much.
Let me just say one last thing. I want to thank so much all my collaborators who are like the most excellent group of people in the world and are such a joy to work with and so brilliant that it's been an honor to kind of represent the group here.
Super, thanks a lot. So a big round of applause again for Charlie Bowman and his team. Thanks. Bye-bye.